Hi, welcome back to EducateTube.com. My name is Sitsuki, your host. Today we'll be talking about quantitative chemistry. You probably wonder, what is that? Well, it's about chemistry, and we're going to quantify the reaction, the chemical reaction we're going to do. So what are we going to talk about? What chemical reaction I'm going to do? Well, it's someone you can do at home, really. I have here baking soda, which is sodium bicarbonate. And I also have here a 5% vinegar, which is acetic acid. So we're going to combine them together, and we're going to predict how much the byproduct is, which is gas that's forming. In this case, we're going to look at carbon dioxide. So you've probably done this before in primary grades and maybe in grade 9 or 10, when you're doing the experiment and figuring out what's happening. But you went only so far, right? You talk about, oh, you mix this together and you mix this together, and yeah, gas is forming, carbon dioxide is forming. So what, right? Once you go to high school, it's like, what's the big deal about that? Well, we're going to figure out today that we can actually quantify it. For example, what I mean by that is, if I put 10 milliliter of acetic acid, 5% acetic acid, and let's say I put about a gram of sodium bicarbonate, right? We're going to figure out how much carbon dioxide is produced. We're going to balance the chemical equation, and then we are going to predict how much the gas is formed, carbon dioxide is formed. And then next video, I'm going to show you if it is true or not, and see if there's some kind of percentage error that's involved. Right? Very interesting. Now we are combining chemistry and math together. Isn't that amazing? Math is amazing with chemistry, science. Now you see why it works. Let's get started. EducateTube.com. Okay, so in today's experiment, we're going to mix acetic acid, which is a vinegar, 5% acetic acid. So I'm going to do that. Okay, and then now it's supposed to be about 20 ml, right, of acetic acid, and then we're going to add about 1 gram of sodium bicarbonate, or baking soda, right? And then we're going to predict, for example, how much gas, CO2, is produced. And that's really what we're going to do. We know that this is a reaction, carbon dioxide is produced, but the hard part is how much, and that's what we're going to learn today. Let's have a look at the equations. Okay, so let's write the chemical equation of these two reactions, sodium bicarbonate and acetic acid, which is vinegar, 5%. So we're going to do that. Let's start out writing the word equation first, then we're going to write the chemical equation. So here's the word equation. You have baking soda, right, which is sodium bicarbonate. So sodium bicarbonate. Okay, or sometimes known as sodium hydrogen carbonate, but we're just going to leave it the common name for now, bicarbonate. And it's going to be added to vinegar. In this case, it's called acetic acid, 5% acetic acid. And when we combine these two together, the reaction, now I don't have an arrow, I'm just going to draw an arrow down like this. Okay, these two together, when combined together, right? It's going to form, well, we know that when in the experiment, when we do this, it's going to form gas. This gas is actually carbon dioxide that's forming. Okay, so carbon dioxide gas is forming. Right? On top of that, sodium, a salt, is produced as well. Sodium acetate. Wow, that sounds like a hard word to remember, right? But I'll show you the chemical reaction, and you'll see that it's not as complicated as you think. Once you see the chemical formula, everything actually makes sense. And then what else is produced? I believe water is also produced as well. Water, or H2O, okay? Or if you want to call the scientific name for it, it's dihydrogen monoxide. Kind of, this is a very hard name to remember. Just call it water then. All right, so that is the word equation. You got this sodium bicarbonate solid added to 5% acetic acid solution, and the byproduct is carbon dioxide gas and sodium acetate salt in solution, and water is produced. Now let's write the equation in the chemical formula equation, okay? Okay, so let's look at the word equation. Sodium bicarbonate plus acetic acid gives you carbon dioxide, sodium acetate, and water. Now let's write the chemical equation, the formula. So Na for sodium bicarbonate is HCO3, and I'm going to write the state, which is in aqueous. Actually, this is in, we'll make it solid because it starts as a solid. Okay, and then acetic acid is in solution. So we're going to put CH3. This is an organic acid. CH3 COOH, and is in water, aqueous solution, and it gives you carbon dioxide, which is CO2, a gas, plus sodium acetate, NaCH3COO, and it's an aqueous solution, and water, H2O. Okay, and that's in liquid form. So that would be the chemical formula for this equation here. Now it's actually balanced. You can check it out. If you check all the elements on the left side and the right side, you'll see that it's balanced. Okay, so this is what happens when you put sodium bicarbonate plus acetic acid. You'll get the gas, CO2, and then the salts, sodium acetate, and then water. Okay, I can go on later on. I'll explain to you why, for example, carbon dioxide and water is produced and how it came about. But for now, let's look at the overall reaction here. Okay, so the question is, it's not like, okay, that's it, right? That's what you probably learned in grade 9, and then you get, that's the end of it. But what I want today to do is to figure out, let's say if I have 1 gram, okay, let's make it more specific, let's say 1.0 grams of sodium bicarbonate, and I added, let's say, I don't know, instead of 10 mils, let's make it 20 mils, okay, of acetic acid, which is 5%. So 20 mils of 5% acetic acid, which is vinegar, right? Vinegar is 5% acetic acid. So how much, here's the question, how much carbon dioxide, CO2, right, is produced? Okay? That's my question to you. I want you to think about this. You know, this is a very hard question if you haven't learned chemistry before. But if you're taking grade 10 or 11 chemistry, this shouldn't be that hard. So take your time now to think about, if I had 1 gram of sodium bicarbonate, I mix 20 mils of acetic acid, 5%, how much gas, carbon dioxide, will be produced? Think about it, pause this video, and then come back to me. I'm going to give you the answer in a couple of seconds, okay? Okay, hopefully you got some form of something writing down. You may not get the right answer, but hopefully you did. So let's attack this question. Okay, you might want to take out your periodic table, look up the molar mass for sodium bicarbonate, and then we're going to figure out how much moles is 1 gram, right? Same thing here. We're going to figure out how much, we're going to first figure out how much mass is 5% 20 mil of acetic acid. We're going to convert that to mass, right, in grams. Then we're going to also figure out its mole as well. Once you find the 2 moles of this too, then we can figure out how much carbon dioxide is produced. That's really the solution to this question. The thing is, of course, you need to find out what the molar mass for sodium bicarbonate is, and the molar mass for acetic acid, right? Now you probably wonder, why are we not just compare based on the mass itself? Because the mass itself does not allow you to figure out how much of this is needed, because this equation is based on the number of particles. What I mean by that is, for 1 mole or 1 particle or 1 molecule of sodium bicarbonate plus 1 molecule or 1 mole. Okay, 1 mole is actually a very big number, but it's a ratio. If we compare, let's say 1 mole of this plus 1 mole of this, you get 1 mole of that, and you get 1 mole of this and 1 mole of that. It's really saying 1 molecule of sodium bicarbonate plus 1 molecule of acetic acid gives you 1 molecule of CO2 plus 1 molecule of sodium acetate and 1 molecule of water, right? So that's what we want. We want to compare it based on moles, the number of particles, right? one molecule of this plus one molecule of this gives you one molecule of that and that and that. So the mass doesn't tell us how much molecule there are. So the balance equation is based on the number of molecules, right? That one of these gives you one of these, one of these, one of this. The mass doesn't do that. So you have to convert the mass into moles, which is a large number of particles. But at least it's a quantity of particles. And then you can figure out how much particle of CO2 is produced. All right, so let's first look at this question and find out what the molar mass of NaHCO3 or sodium bicarbonate, okay? So to figure it out, you have to take your periodic table and find out what the molar mass of sodium is, hydrogen, carbon, and oxygen, all of them, and add them up, okay? So for example, let me grab my periodic table and I'll come back and we will then figure out how much the mass will be. Okay, so here I have a periodic table on my computer here. I'm going to look at that up and then we're going to calculate the molar mass, right? So the periodic table for sodium is 22.99 grams per mole. Okay, I'm just going to lead to one decimal places for now just to save time. Okay, and then for hydrogen is 1.088 grams per mole plus carbon here is 12.01 plus oxygen, there's three of them. Oxygen is actually 15.9999, but we'll make it to 16.0, right, to save time. In fact, I should have made this into, let's make this to two decimal places. Okay, let me make that to 1.01 for hydrogen, and oxygen is 16.0, okay, just to save time here. Times 3, there's three of them. Then you add them up. So 22.9 plus 1.01 plus 12.01 plus 16.0 times 3. Add up the molar mass of these individual elements, and you should be able to get your molar mass for sodium bicarbonate. All right, let's do that right now. Let me get my calculator. Okay, I grabbed my calculator, so I got 22.9 plus 1.01 plus 12.01 plus 16 times 3. The molar mass for sodium bicarbonate is 83.92 grams per mole. Okay, so we are now going to figure out, using this number here, the molar mass of sodium bicarbonate and the mass of sodium bicarbonate. We can determine the number of moles of that is, okay, because what we have is one mass, a molar mass. We can use the formula finding out what is the moles. Okay, the moles is basically mass divided by molar mass, and you'll get the moles. All right, so let's do that right now. So what I have here, I have a mass of sodium bicarbonate is 1 gram divided by its molar mass, which we just calculated using the molar mass of sodium, hydrogen, carbon, oxygen, 3 of them, and add them up, and I got 83.92 grams per mole. When you divide these two numbers together, 1 divided by, okay, let's see, 1 divided by 83.92 grams per mole, I get 0.01. Let's keep it to, okay, because this is only two decimal places, we'll keep it to two decimal places. So 2 significant digits, okay? So it's been 0.012, so 2 significant digits we're going to leave, and that's in moles. Right. So that's how much moles is given here. Now we're going to figure out how much moles is this 20 mils of 5% acetic acid. All right. So this is a little bit harder because we're going to convert it into mass first, and then we're going to convert it into the moles. Okay. Let's keep this, put it at the back of mind. Okay, well, I'll extract this information later on. Now we're going to figure out how much moles is 20 mil of 5% acetic acid. So 5% acetic acid is equivalent to, okay, 5 grams for every 100 mil of solution. So that's how much acetic acid is in 100 mil. 5 grams for 100 mil. Okay, so that, what you want to do now is figure out how much grams is that? So we have 20 mils. It's going to be times 20 mils because we use only 20 mils. So 20 times 5 divided by 100 will give you exactly 1, because 5 times 20 is 100, divided by 100 is 1. So that's 1.0 grams, okay? We'll assume that the percentage, 5% is actually 5.0 percentage, right, for significant figures. So we're going to keep it to 2 decimal places. So it's going to be 2 significant figures, so it's 1.0 grams. All right, so that's 1.0 grams of acetic acid. But we can't compare based on mass. Remember I said you have to compare based on moles. So what we want to do, we take this mole, just like how we did over here. We take mass of moles of acetic acid, CH3COOH, okay? The mass divided by its molar mass. Now you can do what I did before for sodium bicarbonate. Take up your periodic table and add up the molar mass of individual elements, and you get 83.92 for sodium bicarbonate. But for acetic acid, I could do that as well. I could add up individual elements. There's 2 carbon here, so it's 12.01 times 2, and there's 4 hydrogen here, so it's going to be 1.08 times 4, and there's 2 oxygen there, is 16 times 2, and add it all up. But I actually checked the Google, and you'll see that it is, if you look at it, it's 60.05 grams per mole. Okay, so we don't need to calculate that. I just searched for it. Now I can always verify later if that's the right answer. Okay, so that is the molar mass for acetic acid, 60.05 grams per mole. Okay, so 1 gram divided by its molar mass, molar mass of acetic acid, 60.05 grams per mole. And taking my calculator, I get, let me see, 0.01. Okay, I'm going to round to 2 significant figures, so 0, it's actually 0.1665. We'll make it 0.017, okay, and that's in moles. Okay, so now we have 2 number here, okay. You see this is 0.017 moles. So from 1 grams plus 20 mils of 5% acetic acid, we convert that into moles. So we're going to say this is 0.01 moles of sodium bicarbonate and 0.07 moles of acetic acid. Now if you look at it, it's actually supposed to be 1-to-1. For every 1 molecule of that, I'll give you 1 mole. For every molecule of that, you need 1 molecule of that, then produce 1 molecule of CO2. So 1 molecule of sodium bicarbonate plus 1 molecule of acetic acid will give you 1 molecule of CO2. But we are now using the unit moles. Moles is a very big number. Okay, it's an Avogadro's number, which is 6.022 times 10 to the 23rd. So 1 mole, and I have a lot of things that we got to remember. Okay, so 1 mole is equivalent to 6.022 times 10 to the 23rd particles. Right? Another constant we have to remember. So what we have here is 0.012 moles, right, of this, and 0.017 moles of this. Now if you look at the number, it's supposed to be 1-to-1 ratio. You notice that 0.012 is smaller than 0.017, right? The ratio should be 1-to-1. And notice that this is a little bit more than this. Okay, if you do a 1-to-1 comparison, the ratio, you'll find that this is a bit more. And what we call this amount, this extra amount, we call that excess amount. Okay, and this amount here is the limited quantity. So this this compound, this sodium bicarbonate, is the one that will determine how much CO2 will be produced. So we are going to be basing on the amount that is limited, which is this sodium bicarbonate, 0.012 moles. So this will determine how much will be produced. So if this is the limiting and this is an excess amount, so the amount here, because it's 1-to-1 ratio, and we already determined that based on all these calculations, 0.012 is the amount used, right? So, and it's the limited amount, so this determines how much CO2 will produce. And so the CO2 will be producing 0.012 moles, okay, based on this limiting reactant. Okay, this compound reacted with this compound, so sodium bicarbonate plus acetic acid. So this is the limiting amount, and this is how much will be produced. All right, wow. Okay, let's keep going. I told you it's a lot of the calculation. So we haven't answered the question how much CO2 is produced yet. We did calculate it. We go 0.012 moles, which to you and to me doesn't tell us or help us to visualize how much that is, right? In order to visualize it, because gas is usually in liters, right? In liters. So in moles, you want to work with moles. Let's find the number of particles. You just multiply this number by the number of particle in 1 mole, which is 6.022 times 10 to the 23rd particles, times 0.012 moles, and you'll get the number of particles. But that's not really helpful, because really gas is better if we measure based on the normal atmosphere pressure, which is the pressure surrounding us right now, and how much liter is actually made based on that. So we need another equation. Okay, so we need universal gas law to determine how much liter is 0.012 moles. So let's keep going. We're going to erase all these stuff. And we're going to use this number here. We know now approximately 0.012 moles of CO2 is produced. Okay, which, like I said, it's an answer, but it's not something we can visualize. It's not something we can actually say, oh, I have 0.02 moles of CO2, and what's that, right? So what you want to do is convert it to liters, because liter is better to understand, because we have a liter bag of something, right, of gas or something like that, something we can actually hold, right? So that's easier to understand. So let's do that. Well, what you need, the next formula you need is universal gas law, PV(N)R equal to nRT. Okay, so pressure, volume, number of moles, R is the universal gas law constant, and temperature in Kelvin. So we're going to do that. We're going to calculate that. Now, because we want to find the volume, we're going to isolate volume and rearrange the equation. So nRT divided by P is what's the formula we need to use. All right? So we're going to use this formula to determine, and the volume will be in liters. Okay? So how much? 0.012 moles of that in terms of volumes. Okay, let's do that. So let's calculate this new equation here. Volume equal to N, which is number of moles, which we have now, 0.012 moles, times R, the universal gas law constant. It's a constant number. And I'm going to use atmosphere instead of kilopascal. So if you look it up on the internet, you'll see that it's R expressed in terms of liter. Let me see. Under Wikipedia, the R value, let me see now, I'm going to look it up. Yes, so it's 0.082057. Just keep to 7 for now. Okay, we're going to keep to 5 significant figures. And it's expressed in liter. Okay, we're going to use liter atmosphere per Kelvin moles. Okay, so that's the unit that we're going to use is liter atmosphere pressure, Kelvin, and moles, right? So all that units. So the only thing is that we're going to assume that is 1 atmosphere pressure in this room right now. Okay, so 1.0 atmosphere pressure. Okay, that's relatively correct because it's quite constant. The atmosphere pressure at sea level is around 1.0 atmosphere pressure. So let's keep that for now. Okay, so let's put all the number in there. So 0.012 moles of CO2 times R. It's now, look it up, and it's 0.082 057. I don't have to be that accurate, but let's just do that for now. Okay, that's the universal gas constant. Times temperature. Let's assume this temperature here, it's about, let's make it 24 degrees Celsius in this room, okay? If it is, then in converting to Kelvin, it would be 273 plus to 24 Celsius. That'll give me 297 Kelvin. So that's the temperature in Kelvin. We're going to put Kelvin, 297 Kelvin. Okay, divided by the pressure. I said already to keep it in atmosphere pressure, right? 1.0 is the standard atmosphere pressure in this room. Is about that. Okay, at sea level. So we're going to have that. So now, just use a calculator and calculate how much. And that will be, once you calculate, that will be in liters. Because the unit for universal gas constant is liter times atmosphere pressure divided by Kelvin times mole. Okay, that's the unit. So when you calculate it all out, the unit will be left as liters. Okay, so let's do that. Okay, so 0.012 times 0.082057 times 297 we'll divide by 1, okay? That will give me 0.29, and because we only have two significant figures, we have to leave it to that, okay? Because really we can't be too accurate with this one because it depends on how much significant figures we have. So we're going to leave the two significant figures or two decimal places. So 0.29 liters, or that's 290 milliliter. That's how much gas will be produced using 1 gram of sodium bicarbonate, 20 mils of acetic acid, 5%. You'll be able, in theory, we should get 290 milliliter. We're going to do that next time. We're going to prove that if this is correct or not. And I'm going to calculate the percentage error. Is that whether we actually get, or percentage yield as well, not just error. The error is when you do the mistakes. But percentage yield is how much is actually produced versus the theoretical yield, which is 290 mil. So do we really get 290 mil? I doubt it. If we did, I would get 100% yield. That's awesome, right? But you know, in reality, in most of the experiment done in chemistry, you rarely get 100%, right? So let's go and do that. Next time, I'll do the experiment quantitatively, and we're going to prove that we are close to getting that answer based on the fact that we have all these calculations involved. Now, I had a lot of assumptions I made, right? Like, I assume this room is 24 degrees. I assume the atmosphere pressure is 1.0 atm, right? That's some assumption I made. Other than that, it should work out. Thanks for watching. EducateTube.com.